Hey guys, okay, so we stopped the last video by basically explaining that order matters. The inverse function of matrix products will sort of be in the opposite order as the original matrix product. Now we're going to talk a little bit more about criterions for invertibility. So we're going to say that zoom in here, and B are, okay, so we're going to say that A and B are two invertible matrices. They're invertible by themselves. Right? Okay. So from here, the book gives us the fact that B times A equals this identity matrix. So, this means that they're obviously both invertible, right? Because for that to be true, we know that, well, let's see. What do we know? What we know is that inverse of A equals B, and inverse B equals A, right? Because, we've already proved that, when we multiply these two things together, they have to be inverses of each other, right? So, we could write it either in terms of A, where we've got inverse A times A, or in terms of B, where we've got B times inverse B. But either way, it's going to give us the identity matrix. The last thing we know is that A times B is also going to be the identity matrix. So we can prove this. So from the basic definition, we know that if A times B is the identity matrix, and then B times A is the identity matrix, that means that they're inverses. So we can sort of use a little bit of reverse logic, right? Because we know that if A times B is the identity matrix and they're inverses, well, we know that if they're inverses, B times A equals the identity matrix must also be true. This is kind of just what I just pointed out here, right? Like we know that if this is equal to the identity matrix, then these things have to be inverses of each other. And if that's true, then it's got to be, A to the negative 1B, B to the inverse A. But we can have an official proof, okay? So I'll do this sort of fancier official proof in a different color. So to show that something's invertible, we can go ahead and prove that A times vector X equals the 0 vector is true, right? We already proved, or that it has only one solution, that solution being vector X equals the 0 vector. We already sort of went over that idea. We are all kind of tracking with that. So when we sort of follow from here, what we can do to show that A is invertible, we want to prove here that A is invertible. What we do is we multiply B on both sides. So we get B A times vector X equals B times 0 vector. And that's, of course, just going to equal the 0 vector because anything times the 0 vector is 0. So it follows then, we can say that vector X is equal to the identity matrix times X. This isn't anything special. We can always say this, right? Because the identity matrix times anything is just going to be that thing. And then from there, we can say that that equals 0. And B times A times vector X equals 0. So that means then that this is equal to that, which means that A is invertible because X is 0. Obviously, we just proved that. We pointed out that we can say this equals 0. And from there, we can logically say that the B is the inverse of A. And so inverse B is A inverse. And then finally, by this logic, we can also say that AB is also equal to identity matrix N, because if these things are both inverses for each other, then they're going to cancel out either A, whatever order they're in, because we can just say, A times inverse A or inverse B times B, whichever way you do it, they're going to cancel out. So that's sort of our more official proof for this kind of basic idea. And if you want to check this, you can plug it in. You can take BA, right? And you can take actual numbers. We can take any matrix for B and any matrix for A, and we can multiply them together, right? To check that they're inverses, because they should equal out to the identity matrix, right? So if you wanted to go through the process of checking that, you could. Now, nope, just going to scroll. So there are a lot of examples in this chapter. It's a very example heavy chapter. But the example that we're given is we've got 3 n times n matrices. That's too big. Okay, we've got A, we've got B, and we've got C. Okay. So knowing that, what they want us to prove is they want us to show that B is invertible. B is invertible, and express inverse B in terms of A and C. So you might have figured this out already, but we can use rules of association here. And what I mean by this is that we can say AB times C is equal to the identity matrix, right? Because I should clarify that we're given that ABC is the identity matrix. So we can start to associate. We can put A and B together, right? But then from there, because we know that these two things have got to be, or because we've just seen that thing that B times A equals identity matrix also means that A times B is identity matrix, we can flip these around. We can say C of AB equals identity matrix, because that's still true, right? And then we can do association again to say C times A parentheses times B is equal to the identity matrix. Well, for this to be true, that means that this right here is a little grouping, and this right here is a little grouping. And for them to be the invert to identity matrix, that means that this B has to be the inverse of CA. So B is invertible, and B inverse is equal to CA. So that's kind of our solution here. And that's what it just takes what we did and it puts it into practice by using some association. So now we're going to talk a little bit about the idea of a determinant and what that has to do with all this. So I should first make sure that we've kind of realized by this point that, we've already kind of looked at this idea of using a determinant to sort of determine whether something's invertible. We've used this in other examples, but now we're going to deep dive into this a little bit more. So we've got an arbitrary 2x2 matrix where A is equal to, surprise, surprise, A, B, C, D. That should be a D. Okay. So we want to figure out the product of D, negative B, negative C, A times A, B, C, D. And then from there, they want us to figure out when A is invertible, and if so, what inverse A is. So we compute that product, right? We do our, rules for matrix products. And what we get is that AD minus BC, 0, 0, AD minus BC. You know what? I'm gonna need to take a second to grab my charger so that this computer doesn't die on me in the middle of a video. Okay, all good. So we multiply these out, we get to here. So another way that we can write that is we can just pull out the AD minus BC and times that by the identity matrix, because that's just going to give us what we have right here, right? So we can sort of flip this around, right? Because if we know that AD minus BC doesn't equal 0, what we can write is this 1 over, and this should look really familiar because we've dealt with this before. Okay, so let me go back and kind of explain this here. Okay, so we've said that these two matrices multiplied is really equal to this, right? So what we can kind of say here is that we can divide, right? We can divide AD minus BC by this right here. And when we divide that, obviously we get 1 over AD minus BC times all this is equal to this identity matrix, right? And we can sort of say that this whole thing right here is our B and this whole thing right here is our A. Well, if that's true, it's pretty simple here to realize that A is invertible, right? Because, you know, we've got the identity matrix here, but the inverse is going to be equal to this whole section. That's the inverse of A, right? B has to be the inverse of A to make the identity matrix true, right? And then conversely, we can kind of say that if A is invertible, then, so let's say that we know that A is invertible. Well, then we multiply D negative B. That was not meant to happen. No, okay. D negative B negative C A times A B C D is equal to A D minus B C times the identity matrix. This is the thing we've already figured out. We already just talked about this. Well, if we want to, here. Okay, I apologize. My computer's being a little ornery, but it's nothing we can't handle. But what we can do here is we can multiply by inverse A. And then inverse A here. And of course, that means that these two are going to cancel out. And so what we'll be left with is D negative B negative C A equals AD minus BC times inverse A. So here's the thing that we have to realize, though, is that because some of the scalars right here, A, B, C, D, are non-zero because they're the entries of an invertible matrix, well, it follows then that AD minus BC can't equal 0, right? Because if AD minus BC equals 0, right? If this equals 0, then 0 times inverse A would equal 0. And we can't have this matrix equaling 0 because this matrix doesn't equal 0, right? So in other words, AD minus BC cannot be 0 and still have an invertible matrix, right? So I'll sort of give the theorem here, and then I'm going to cut us off and come back with the next video that will go a little more into geometrical interpretation. So our theorem, if we've got the matrix A, B, C, D, it's invertible if and only if AD minus BC does not equal 0. AD minus BC is the determinant. The determinant of A is AD minus BC. And part B of this theorem is that if we've got that matrix A equals ABCD, and if that's invertible, then the inverse is going to be 1 over the determinant of A times D, negative B, negative C, A. Okay, so basically this video, it talks about criterions for invertibility. It sort of proved that. It gave a couple of examples, and then we sort of proved this idea of the determinant having to do with invertibility. So I'm going to stop the video here, and I'm going to come back with some geometry.